All right, next topic is to describe the structures of alkenes. These compounds with double bonds in them are going to have new features that were not present in the alkanes. These compounds, due to those double bonds, are going to have a new characteristic that we describe as geometric isomerism. Their isomers are based on different geometry. The double bond geometry that you get around carbons with 4 bonds and 2 of them are a double bond, there's going to be a 120-degree angle. We called this trigonal planar geometry, if you remember from previous course when we described the shapes of molecules. When you have 3 bonding regions around the central atom, it becomes trigonal planar with 120-degree angles. These are very rigid. They do not rotate. And if you remember having used models in lab, perhaps, you cannot rotate a bond that's a double bond because it's definitely rigid. The models represent that reasonably well. And so the 2 isomers here are shown are different in the position of the substituents relative to the double bond. Okay, so what do we have? We have CH3, we have CH, we have a double bond, we have CH, and we have CH3, right? Do we have the same thing here? But yes, we do. But it's not the same because you can see that the shapes of the molecules are different. And it's different of the position of the substituents, namely methyl groups in this case, relative to the double bond. And now we have to explain what those are called. These isomers are named as cis and trans, and you can think back to Bruce and Caitlin Jenner if that helps you. And it has to do with where we put the substituents. So they're isomers because they have the same molecular formula but different structural connections. And in the case of the cis isomer, the methyl groups are on the same side. Cis, in a sense, means same. Same side of the double bond. If you're thinking about the double bond going across the middle, they're on the same side, in this case, the top. And the trans isomer is the one that is opposite. And if you've heard about cis and transgender, you got that figured out. So they're relative to the double bond, the methyl substituents here, and more specifically, the longest chain is going to be on opposite sides. The longest continuous carbon chain is going to be on opposite sides of that double bond. What else is attached to the carbons of the double bond does not matter. You're always going to be paying attention to the longest chain. It's a good place to focus your attention. All right, so having said that, what can we do with it? We're going to make some generalizations and figure out how to determine if a compound is going to have these geometric, aka cis-trans isomers. The answer is no, if one end of the double bond has identical substituents, such as this one on the left here, 2 things the same. You can draw the longest chain 2 ways sometimes, or if you switch the ends, nothing changes. Let's look at another example. If you switch the ends, in other words, if you have to turn this cis into trans, you'd have to switch these 2 ends to change it. Well, this next example, if you switched this down to here, you still have the same compound. It hasn't changed anything. And or you can look at the compound on the right and just flip it, and it'll look exactly the same as the one on the left. So there's not isomers when 2 things, substituents on one carbon of the double bond are the same. But if the 2 substituents on each end of the double bond are unique, if they are switched and you get a new structure, then you do have cis and trans. So if you switch this hydrogen down to here, then we have turned compound 1 into compound 2. And looking at the longest chain, all on one side, we call this cis. And the longest chain on opposite sides, we call that trans. Those cis and trans descriptions will precede the names of the compounds. Now, in this case, what is the name of the compound? Well, how many carbons do you have? 1, 2, 3, 4, 5. Both of them are pentene. And so we start with what we know. Then we describe the position of the double bond. In this case, it starts at carbon 2. And the other thing we need to know is the geometry. So it's just cis. There are no extra branches here. The second compound would be described as all the same except that it's trans and 2 and pentene. All right, another example. These things take practice. Do these compounds have names, and can they be described as cis and trans? First of all, let's see what we know. The first one has a longest chain that you have to look at for a few minutes to figure out where it's going. And if you wanted to choose to go this way, that would give you 1, 2, 3, 4, 5, 6 in the longest chain, which would be the same as if you went this way. Ah, there's a clue. If you go 2 different ways and get the same longest chain, there's no cis and trans. Because if you switch this group with this group, you get the same compound. It's just the same thing. We flipped it and nothing new results. So there's no cis and trans here. 6 in the longest chain means the last name is hexene. And we're going to pick to start numbering to give the double bond the lowest numbers. And that means I'll start over here with 1, 2, 3, 4, 5, 6. That means we're going to have to name what else is on there, but the double bond carbons begins with number 2. And then the other fragments to be named in this compound are going to be noted this way. I'm going to make a box. That's a methyl group, and that's a methyl group. There's 2 of them. So that's dimethyl. And what numbers are the methyl groups on? One is on 2, one is on 4. So 2, 4 dimethyl 2-hexene. Does the compound at the bottom have a name, and is there cis and trans? Well, if the 2 substituents on each end of the double bond are unique, you could switch them and turn the compound into something new. In this case, those 2 are unique. They're not the same. And on the other side, whoops, those 2 are not identical. Now, the fact that the left looks like the right does not matter. That's not important here. Let's see if I can erase that thing. There we go. Oops, return my tool. The fact that the left looks like the right does not matter in that sense, but what's on each carbon of the double bond is what's important. So on the lower structure, we need to decide where the longest carbon chain is. We're going to go this way to find the longest carbon chain. I think that looks right from most people's standpoint. And the pieces that are in the longest chain have which shape? Are they on the same side or opposite sides of the double bond? It looks to me like opposite. So this would be described as a trans geometry. The longest carbon chain, this molecule is highly symmetrical. So you can start from the left, you can start from the right, you'll get the same thing if you stare at it. So I'm just going to go from the left for simplicity. 2, 3, 4, 5, 6. So it's a hexene again. Seems like they're kind of common, huh? They're not too crazy large. The double bond begins with carbon 3. But what else we have to label in here are the extra pieces that are not in the main chain, and that's methyl groups again. So trans is the very first part of the name, and the location of those 2 groups has to be specified, 3 and 4, and it's dimethyl preceding the 3-hexene. Lots of pieces, but legit. Notice that if you were to redraw this compound, let me see if I can do it to make sense here, with the double bond like this and switch the compounds of the groups on the right, the substituents are still 2 methyls off the middle carbons, but this one instead would be the other isomer. There we go. That would be the cis isomer of the same compound. In other words, I have switched the substituents on the right end of the double bond to get that structure. All right, there are many, many examples. I hope this is helpful to you. Please ask lots of questions. Good luck on your homework, and I'll see you in class.